So the next speaker is Alex Matthews, and he's going to speak on something that seems to be a very hot topic at the moment again, and has been in Cambridge, I think, a long time ago, which is Bayesian neural networks, and in particular, how to choose priors for Bayesian neural networks.
Okay, thank you, Sebastian. Can you hear me? Yeah, good. Okay, so this is a hard problem. I'm going to share some recent thoughts about it from 3 papers. I'm going to primarily concentrate on the one at the top, but I'll have a little bit of time to talk about some ideas from these 2. But there's a lot more in these papers than I can talk about in this amount of time. Okay. So Radford Neal challenged us to think hard about our priors for Bayesian neural networks. If you don't think hard about your prior, then you're putting junk in, and you shouldn't be surprised if you get junk out. And that's even if you do a perfect job of your Bayesian inference. So if you have a perfect approximation algorithm, if you put junk in, you'll get junk out. Okay, so it's desirable to add capacity to neural networks. Intuitively, a large enough network can model a broad variety of functions, and you can formalize that and make it rigorous. Often with neural nets that are used in industry, we choose our architecture using multiple runs, perhaps thousands, validated against some held-out data. A really appealing aspect of the Bayesian approach to this problem is that it incorporates Occam's razor. So you can make your network very big, and the magic of Bayes will correctly choose some complexity of prediction depending on how much data you have. But it's not totally magic. Care is required in making the network large, and that's whether you make it wide or deep. Okay, so the classic result in this area is that of Radford Neal. And he studied neural networks with one hidden layer which were fully connected. And I've drawn it in a slightly strange way here to emphasize the difference between the pre-nonlinearity and the post-nonlinearity. But this is just a standard single hidden layer network fully connected. I've written out the shapes for you. So here, n is the number of data points, d is the dimensionality of the data. So you can stack that all together. You can imagine passing through a data matrix. And what you'll end up with is some row vector of size n. Okay, so a row vector which is of the size of the amount of data you fed through. Okay, it's a compact way of writing something that should be familiar. So we need to carefully scale our prior. In particular, these weights here need to have 1 over k scaling, where k is the number of hidden units. So that if we make this large, we don't get variances that either blow up or collapse. And what Radford Neal showed was that if you take this vector of data function values at the end, as you increase k to infinity, this thing will converge in distribution to a normal distribution with mean 0 and covariance c. And don't worry too much about the details of this, but the elements of this covariance matrix are some expectation taken under the nonlinearity, and this x star i and x star j indicate the corresponding data rows of the matrix. To prove that, you need the standard multivariate central limit theorem. So the big contribution, I guess, was to recognize you wanted large capacity and to then realize that you could apply the central limit theorem in this context. Okay, I wanted to really go into a bit of detail on the central limit theorem. Maybe this kind of seems obvious to people. But I think it's important to realize that it says something really quite precise, right? So convergence in distribution means something really quite precise. It means that there are several equivalent definitions, but the one we can talk about is that the cumulative distribution function will converge at all points where it is continuous. Right? So are we sure that we know what convergence in distribution means? Because it means something quite precise. Now, if you were sure you knew what it meant, OK, fine. So the central limit theorem for a one-dimensional random variable for a sequence here, and their IID with mean 0 and finite variance sigma squared, if we define this standardized sum, Sn, where the standardization is by root n, then this Sn converges in distribution, in the sense I've described, to normal 0 sigma squared, i.e. sigma squared is your variance. OK, so I'm sorry if that was familiar to you, but here's a question then. What does it mean for a stochastic process, i.e. an infinite dimensional thing, to converge in distribution? OK, there are actually several definitions in the mathematics literature. A reasonable one for the uses in machine learning is that all the different finite dimensional distributions should converge in distribution. And that's the one that we use in our work. But it's not at all obvious that this is the only answer. In fact, there are many different answers. I can give you more detail on that offline if you would like. OK, so we're going to go back to our diagram, and we're going to add multiple hidden layers. And we're going to update the recursion in the normal way. And again, I've written out the shapes of these things for you. Again, we end up with some row vector of size n, the number of data points we fed in. And when we carefully scale our prior this time, we're going to have two hidden unit numbers, k1 and k2. And the interesting result is that as you take this limit here, with both of these tending to infinity, then this thing converges in distribution to a multivariate normal with mean 0 and covariance matrix C2. Again, don't worry too much about the details of how this covariance is defined, but notice that this second covariance matrix is defined in terms of recursion on the first one. So it has as inputs the covariance matrices you had from the first layer, and in that sense, you can see that reflects the deep structure of this network. Now, the proof of this is very much harder. It doesn't rely on the standard central limit theorem. And we talk about that a lot more in the paper. We're not the first people to think in this general area. In fact, there are some really important works here. And I would highlight also that simultaneous to the ICLR paper that we had accepted, there was also one accepted from Google Brain, which had some overlap with our work. So when we looked over this really good literature, there were two things that we felt were perhaps missing. So the first thing that we felt was missing was that, OK, so this applies to infinite networks. But presumably if you have a fairly wide network that's fully connected, it should somehow be fairly close to a Gaussian process. So if you're working in Bayesian neural networks, perhaps it's possible in some instances that what you're doing is actually very close to a Gaussian process all along, if you were using these kind of fully connected networks that we've described. So we thought we'd have a look at that, right? And we've got lots of experiments in the paper, and we're going to do more. The second thing that we thought was perhaps missing from the literature was a really careful mathematical treatment of this proof that I described. I think we improved the status of the literature on this, but we still had to make some strong assumptions when we made our proof, and they're stronger than we think are necessary. And indeed, our experiments are done without having to make these strong assumptions. And we made a conjecture in the paper that this behavior would be really general. Physicists talk about universality. And in fact, since we submitted this paper, we've been working on our conjecture, and we believe that we have it. We'll be submitting that for peer review in the next few months. OK. We can measure the rate of convergence. So there's a couple of metrics you could use. We used MMD. So you can look at the distribution of the function values of the neural network with some finite number of hidden units per layer and compare it against the corresponding limit GP. And here we've done it for 1 hidden layer, 2 hidden layer, 3 hidden layers. And you can see they all have a convergence property, but that it happens slower if you have more hidden layers. In this case, the 3 one is getting there slower. So why are we putting all this hard effort in, right? The mathematics in particular has required quite a lot of work. Well, we think that it's important to know about this. Any Gaussian process can be viewed as a linear model on some feature space. That says that the covariance between the function value at x and the function value at x dash can be evaluated as an inner product of some feature vector psi acting on x and x dash. That's a standard result in the theory of kernels. Well, that's an issue in this context, right? Because the representation, in terms of this psi, is not being learnt from data. And generally, I think representation learning is viewed as quite important. Indeed, deep learning was created as an attempt to get round the limits of kernel methods. And there are these no flattening theorems, which say that if you have some kind of wide circuit or neural network, then it has certain expressivity problems that can be fixed by choosing a deep circuit or network. So, in a given modeling problem, we have a situation where either Gaussian processes and kernel methods are better than we thought, and presumably there are quite a lot of problems where they do work well, or we should be avoiding this limit behavior by choosing priors that don't match the conditions necessary for the onset of the central limit theorem. Obviously, this any given modeling problem aspect means that we need more empirical work. And I suspect for AI problems that 2 is going to often turn out to be the right answer in this context. And indeed, I would be saying this more strongly, except the Google paper I mentioned happened to get actually some surprisingly good results with these Gaussian process kernel methods. I think we still need to get to the bottom of that. OK, so I can talk a little bit about extrapolation properties as well. So if you look at the kernel that you get from the ReLU network, and you look at the kind of standard RBF kernel that GP people tend to default to, they both give reasonable behavior near the data. If you zoom out, you find that they have drastically different extrapolation properties. So the RBF tends to 50-50, whereas this ReLU kernel is still very confident a long way away from the data. And indeed, if you were looking at this in isolation, you would say, well, this seems like the more sensible thing to do. How can I be so confident out here? And notice that both of these are Bayesian models, right? And it's not just GP models that do this. You get this with more standard Bayesian neural networks. With ReLU networks, you tend to get this confident extrapolation. OK, so I said, well, it seems undesirable here, but it's known that RBF networks in high dimensions, so Gaussian processes in high dimensions, aren't going to extrapolate well at all. They suffer from severe cursive dimensionality problems. So maybe in high dimensions, we need some of this behavior. So perhaps the thing to do is try and get the best of both worlds, get some compromise between very confident extrapolation and something that doesn't extrapolate at all in high dimensions. And that's kind of the motivation for this work that we did with John Bradshaw was leading, and you can check out that to see how we approach that problem. I would say it's difficult to get the best of both worlds, but I think we've made some progress in that direction. OK. So I'd also like to talk about the dangers of improper priors. So if we take the network that we were working with before, and we use a different prior for the weights, where we just take some constant over the abs of the weight value. OK? Well, you say to me, why would I take that prior? Well, people in the literature are using this prior. it's an improper prior, right? So this C is in some sense not definable. You can't find a C for which this normalizes. Okay, and sometimes people do use improper priors, right? But almost always when you use an improper prior, you would expect to end up with a proper posterior, so a posterior distribution that normalizes. But actually, we recently showed that this one doesn't normalize, right? So you end up with something that doesn't even normalize in the posterior. Okay, well, why were they looking at this prior? Well, they were trying to recover Gaussian dropout as a variation approximation, and it led them to consider this prior. But, you know, you really have to be careful when you're thinking about these priors, because as I say, they can have some really strange properties. And you can see the work with Jerry Cron that we did for more on this. Okay, so I'd like to mention my brilliant co-authors who are all up here. And again, these are the papers that I was talking about. As I say, there's a lot more in all of them than I had time to relate. I guess I probably have some time for questions.
Time for questions? Can I start with one?
Yes.
So the Bayesian paradigm is usually conditioned on assuming some type of model.
Mm-hmm.
And in this talk, you focus on the prior choice. Now, if I look at the innovation in deep learning in the last 5 years, a lot of this innovation comes out of choosing different architectures, refining architectures, adding this, adding skip connects, or whatever. Do the tools that you have developed, can they also make some guidance or give some insight into the problem of choosing the architecture, which seems to me a very big issue, given some application problem?
Yeah, I think that's a very good question. And although it's not one I've worked on much, this choice of structure, I think it's one that, you know, fits naturally into this paradigm. So one thing to say, with a convolutional network, you can view that like a fully connected network where there's some tying in the weights, right? So in effect, you know, you're absolutely sure that these weights should have this shared value, right? And it's important to note that really most of the impressive empirical successes of deep learning have come from these structured models. So recurrent networks and convolutional networks all put in structure that is very natural to the problem being considered. But a lot of the theoretical arguments that kind of launched deep learning, particularly from Yoshio Bengio's group, should apply to these kind of fully connected networks that we're talking about. But yes, I think that there also needs to be work looking at how a Bayesian should incorporate the structure that we know is really important for getting empirical success.
More questions?
Yeah?
Is there any evidence that when you train, then you play a Gaussian process? Or does non-Gaussian as you merge when you train, or is there evidence of this?
That's a brilliant question. Yeah. So the experiments in our paper were restricted to thinking about sort of Bayesian models where, you know, the prior and the likelihood fully specify the model. But as you point out, at initialization, effectively, even kind of common networks used which aren't Bayesian in the literature, they use these kind of these random initializations, which in fact look a lot like the scaling that Radford Neal was using. So the MSR initialization, I could talk about that here, right? So that uses that 1 over root scaling that you need. And indeed, the Google paper, those guys have been thinking about signal propagation through networks in these terms too. The second question is that, you know, when you start training, does the Gaussian process behavior stay? That, I think, is a good open question. So one of the interesting things, again, about that Google paper was that they, instead of comparing to like Hamiltonian Monte Carlo in a Bayesian method like we did, they looked at what happened with SGD when they compared to the Gaussian process. And there's a lot of interesting literature trying to interpret stochastic gradient models in terms of a Bayesian approximation. Indeed, stochastic gradient non-Jevon dynamics is one of the things that started us thinking about that.
Maybe a last question while the next speaker sets up.
Alex?
Hi.
On what you did with John, do you think it's important that you get this sort of linear extrapolation outside, or that it might be that the strength of where you comes from linear interpolation, basically interpolation rather than extrapolation?
Yeah, I mean, so it depends partly how your training and test data are generated, right? So, when we set up our experiments in machine learning, we make sure that we kind of have a similar train and test distribution usually, right? But, Zubin always says when he speaks, right, this is a big lie in terms of applications of machine learning. So, if you train a convolutional network and you use it in a self-driving car, there's no guarantee that that's true. And so extrapolation starts to become very important there. And maybe you can't expect networks to extrapolate, perfectly on things they've never seen, but they should at least know that they're wrong, right? Yeah. Okay.
Great. Let's thank Alex again for a great talk.